Hi everyone, this video is on free body diagrams. We talked about this before March break. This is what the handout looked like. It gave a few instructions on how to draw them. And then we drew a whole bunch. Okay, so this is just the front page. We had a few more pages where we drew a lot more free body diagrams. So this is what I'm going to be reviewing in this video. In addition, if you would like to read a tutorial from the textbook, that's on page 117. That's found in chapter 3, section 1, so 3.1 in the textbook. And just as a reminder, we have online access to the textbook. You can log in with the instructions given on Google Classroom under the General Information tab. So on page 117, and actually, so question 1, draw a system diagram and a free body diagram for each object in italics. A book is at rest on top of a desk. So a system diagram is just a regular diagram of the situation. So there's my book on top of a table. I'm not too concerned about the system diagram. I'm more concerned about the free body diagram. And this is how you do it. You first start by drawing the object, and I always want you to use either a box, a circle, or a dot to draw the object. So for a book, I'll use a box. And then you draw an arrow for each force acting on the object. The arrow should point in the direction of the force, and the relative sizes of the arrows should be kind of accurate. So for this book, there's two forces acting on this book. There's the force of gravity pulling it downwards, so there's a downwards arrow, and always label each arrow with the force. So Fg for gravity with the vector arrow. And there's also a normal force from the tabletop, and that would be pointing upwards, and I'll label that F sub n. Now in terms of the sizes, these two forces are equal because the book is not moving, so everything is balanced out. So maybe I'm not going to use a ruler to measure them. I'm just going to indicate to the reader they're equal by putting those tick marks there. But another way to tell the reader that they're equal is simply by writing out a statement such as this. So this statement says that the magnitude of the force of gravity is equal to the magnitude of the normal force. It's important to have the magnitude bars there because the vectors are not equal. Okay, if I were to just say that the vectors were equal, that would be wrong because even though they're the same size, one of them points down and the other one points up, so they are not technically equal. So you got to have the magnitude bars. That's a correct statement. All right, part B, a basketball falls through the hoop. A basketball is always a good example. So there can be my hoop, there's my basketball. That's a bad drawing of a basketball, but it falls through the hoop. Now for the free body diagram, you got to draw the object, draw the basketball, either a box, a circle, or a dot. I'll use a circle for a basketball. And this one's a lot simpler. The only force acting on the basketball is the force of gravity, which points directly downwards. And that's it. Okay, that's all. A few wrong answers. This would be a wrong answer. Okay, because the force of gravity is pointing the wrong way for that answer. The ball might be moving that way because the ball moves in a nice, for a good basketball shot, the ball moves in a nice arc. So maybe on its way down, it is going diagonally. However, the direction of the force, it doesn't matter which way the ball is actually moving. The direction of the force of gravity is still down. All right, in C, a large trunk is being pushed horizontally from behind toward the east across a rough floor. So I'll draw my floor, I'll draw a trunk. Here's my trunk. It's moving to the east, so let's just say that the east is to the right. And someone's pushing it from behind. All right, so there's my system diagram, free body diagram. I gotta draw my object, my trunk, either a box, a circle, or a dot. I'll use a box. The box has mass, so there's the force of gravity going down. It's on a floor. I'm going to assume that the floor is horizontal, so the normal force is perpendicular to it and vertical. They're going to be the same size. The person pushing it, we call that force an applied force. That'll be to the east or to the right, F sub A. And then there's a force of friction because it says it's a rough floor, so there's friction there. That's going to be resisting the sliding. So to the left, F sub F. Now, I drew the applied force and the force of friction the same size because I'm assuming something. I'm going to assume that the box is moving at a constant velocity. The question does not say that. It doesn't tell me if it's accelerating or not. So then I get to choose. And I'll choose it going at a constant velocity. And whenever it does that, it means that the forces are balanced. That's Newton's first law, which we'll review in the future video. All right, so that's a free body diagram there. I can write these statements as well. Force of gravity is equal to the normal force in magnitude. Applied force is equal to the force of friction in magnitude. Question. Figure 6 shows a system diagram of a block sliding up a ramp. A student draws the free body diagram. Discuss the validity of the free body diagram. Okay, so you got to read this really carefully. I circled the word up. Okay, the box is actually sliding that way. It's not sliding down. So maybe somebody pushed it and now it's sliding up. All right, in terms of the free body diagram, we're asked to critique it. I see the force of gravity pointing straight down. I like that. Okay, we should have a force of gravity pointing straight down. I see a normal force pointing straight up, and I don't like that because the normal force should point in a direction that's perpendicular to the surface. So it should really be pointing at some kind of an angle that's perpendicular to the ramp that it's on. I have a force of friction pointing parallel to the ramp and down the ramp. I like the direction that it's drawn because it's resisting this upward motion. However, I don't like how long it's drawn. I think it's drawn kind of too long. Maybe, maybe not. Okay, there's not that many details in the question, but I'll probably draw it a bit shorter when I draw the correct free body diagram. Why is this block moving up? Well, probably somebody pushed it. So you may wonder, should I be drawing an applied force? And I would say no. I would draw one if the person is still pushing it, if their hand is still on the block. But if the hand is off the block, they've let the block go already, then there's no more applied force. So we'll leave that out. Okay, so the corrected free body diagram, I have my box at an angle because it's on a ramp. I'll draw the force of gravity down. I'll draw a force of friction. I'm going to draw it a bit smaller because I don't think it's going to be as big as the force of gravity, which they drew that in the original diagram. And finally, the normal force is what really needs to be fixed. It needs to be on an angle perpendicular to the ramp. It also needs to be of a certain size, which I'm going to explain now. So how long am I going to draw this normal force? Well, I actually first need to do the following. What I'm doing is I am splitting the force of gravity into perpendicular components. Okay, one component perpendicular to the ramp and one component parallel to the ramp. I'm going to call one of them the y component, FGY, and the other one the x component, FGX. Okay, by doing that, I can now have a better idea of how long I'm going to draw the normal force. I'm going to draw the normal force to be the same size as FGY. So I'll make a tick mark there in green. There you go. Those two should be the same size because the block is not, it's not going to fly off the ramp. It's not going to go through the ramp. It's just going to go parallel to the ramp. So there should be no motion in the component that's perpendicular to the ramp. That's why those two have to be the same size. And I'll write that out so to make it absolutely clear to my reader. Magnitude of the normal force equals to the magnitude of the y component of gravity. And there you have it. There's a few examples of free body diagrams. If you want to practice, you can try them on page 122, number 5. Okay, that's still in section 3.1. So you'll have to navigate the online textbooks to get to that section and page, and you can try out some free body diagrams. If you want some feedback on whether you're right or wrong, there's two options. I will make a hand-in folder on Google Classroom. Where you can upload pictures of your free body diagrams, and I can give you feedback on them. But the easier way to give feedback is to probably send me an email with your free body diagrams, and then I can reply giving you feedback there. All right. I will see you next video.